Hello, everybody. Hopefully you can hear me all right. I'm trying a new setup here today. Welcome, welcome, welcome. Today, I am here to talk a little bit about robot movement and human movement. I'm actually here. And by the way, pop in the chat questions, comments, thoughts, feedback. If you're, make sure you can hear everything okay. I tested this earlier. It seemed to be working. Bit of an experiment. In any case, looks like we have a little bit of a delay. I imagine there's probably a 10-second delay or so between when I see your comment and when I can respond to it, I would say. Okay. Anyway, I hope you're all doing fantastically today. Loud and clear. I'm just finally getting from Amish Fonzie. Thanks for popping in and letting me know. But in any case, I hope you're doing fantastically. So, like I mentioned, today we're going to talk a little bit about robots and human movement. So maybe I'll just start by pulling up a little, let me see if I can pull up here. See if this is working all right. Let's do a little bit of a robot video. Let's start with this one here. I imagine people have seen robots that look like this in the past. This one actually is probably the most common humanoid robot that you see around. And this video is amazing. Came out last year, about last year. Let me pull it up again. So where it's called it's a Unitree G1 humanoid, okay, and it is trained to do this little maneuver. All right, so there's a lot going on here. So this robot looks like it's not looping like the way I want it to do. Anyway, we'll just keep doing it like this. So this humanoid you'll see everywhere because you can buy it relatively cheap for a humanoid robot. And I say relatively cheap, so brace yourselves. This will cost you about $14,000, this robot. But compared to what humanoid robots used to be like, back, I would say less than like 10-ish years ago, it would have cost you about $500,000 to buy a robot that could do things, anything remotely this powerful to do like this. So so the costs have come down so much. So you have so many people buying these robots and research labs trying to get them to do cool things. And this little maneuver it'll do right out of the box. All right. So question is, how is it doing all that? All right. And people will see videos of these robots and be rightfully amazed. It's incredible. It's moving like a person, right? And that's not the only example. Let me pull up another example for you. Okay, I like this one. All right. So, all right. Let's see if I can get this to work. All right, here we go. This one, look at this. This is the Unitree G2. This is the next model of robot like that. Yeah, this is pretty good. They're doing quite well. Look at that. Let's do it. This one did a little kick flip, or I don't know martial arts maneuvers. I don't know what these are called, right? And this is incredible, right? And you're like, wow, humanoids can do anything. If they can do that, they can do anything. One more time here. All right, look at that little jump kick, boom, right? Nice, very cool. So again, looks pretty awesome. All right, and further, you might see a video that looks like this. Let me pull up this one here. This is the Tesla Optimus version 3, generation 3 robot. This is, this is out of Tesla, and this is their humanoid robot, and it's doing this little kung fu routine with a person. Look at this. It's bopping back and forth. It's actually seeming to exchange maneuvers, and it looks so impressive, right? Okay, and it is impressive in a lot of ways, but you got to understand what it's doing and why it moves like a person, okay? First off, this robot, let me run it one more time. One thing you'll notice with this video, okay, good, it's looping, fantastic, great. This robot is just performing a pre-established choreographed routine. Literally, it's got a series of moves that it does, and the person right there is playing along with it. This is a pre-choreographed routine, and the person is basically playing along with the routine. The robot has basically only programmed to do two things, and two things only, okay? One of which is do the routine, and this has already been recorded by motion capture, probably of this exact guy doing this maneuver. And so number one, do the routine, and number two, don't fall down. Okay, if you'll notice, maybe be able to see this in just a second here. Okay, when watch the robot's feet. Let's take a look here. Oh, right there. Okay, you saw its feet. Let me just restart it from the beginning here so you can see it again. Okay, its foot's gonna wiggle. Its right foot's gonna wiggle a little bit. Okay, that's a smart little maneuver that the robot's doing to catch itself, to balance itself so it doesn't fall over. Okay, and that's the only two things that the robot is trained to do. Okay, the robot right in here is probably not using vision at all. Yes, there are cameras on board the robot, but almost certainly is not using them for this maneuver. And even when that guy pushes the robot, it's using its balancing routines just to stay up. Very impressive, but it's made to look as though this thing is interacting with a person, when in fact it's just a pre-choreographed routine, right? So, and the reason it moves like a person is because it's literally programmed to move exactly like a person. Those are the exact specifications of the programming. Now, how does it do this? Okay, it's been an incredible advance in robot control in the last handful of years that allows us to program robots to do these cool things. We've been programming robots to walk for a long time. Okay, I'll just show an example from my own research. Let me see if I can pull this up here. All right, so let's get rid of this one, pull up this one. All right, here we go. This is okay, it looks like I might have, all right, let's see, make sure we're doing everything all right. So anyway, so we have this, I have to pull, it looks like I've somehow managed to get rid of my live stream. Hopefully I am still streaming for you all. I didn't lose that fact. I think I probably still am. Just give me a second here. See if I can get back to my stream. Oh my goodness, technical difficulties. I'm probably, I just can't see your comments right now is the only thing. All right, so let's try this again. So anyway, if you can still hear me, let's see. You can see, yeah, I see the issue here. So this robot is walking in a sense like a person. It's got no head. It's supposed to have head and arms, but this is what we got to the project before we finished the head and the arms, okay? Before the head and arms got in the robot, right? This is actually a project I worked on, okay? And it was getting this robot to walk. This is 10 years ago, this robot was walking, all right? So let's see if I can get this going. All right, let's loop this. That's what's going on, fantastic. All right. Little technical difficulties. We will work it out. Control-Shift-6. There we go. Done. All right. We're working out the bugs here. Let's see if I can go back to our home page here. Excuse me. All right. Because I don't want to miss your comments. So I got to figure out a way to get back to your comments. In the meantime, feel free to start plopping things into the chat. Let's go to live video. All right. Good. I'm back. I think I'm back. Yes, I am. I can see you again. Fantastic. I'll just be careful with that. So that robot, the purplish robot that's walking around, that robot was walking 10 years ago. And it was using completely different types of computer code, of computer programming, than the robots you saw doing the kick flips and things like that. This robot, we went through a lot of effort to make walk, and in a way that ended up walking like a person. But there was one key difference from the other robots that you saw. Those other robots were told explicitly, here's a motion of a person. Mimic that as close as you can. When we did it differently, okay? We told the robot, try to be as efficient as you can when you walk. And what happened when we put it through the algorithms? It came out with that motion. Because one of the things that we do as people when we're walking around is we put a lot of effort to not putting in effort. We try to walk around efficiently. Let's take a look. All right, some questions. We got something here. All right. Question. Future of AI learning is from that rally guy. Future AI learning integration into on-the-fly programming. So I'm assuming the question is, can you do programming on the fly so you change the task on the fly? Yes, you can. There are actually existing methods to change the task on the fly. We can pull up maybe some YouTube videos. I have it set up so I can drag some YouTube videos onto the frame to show you some examples. In fact, let me see if I can put, I'll try to see if I can search for these on the fly. It'll be a challenge, but we'll see if we can make it work. All right, let's see. YouTube. So there are some existing methods. All right. In the meantime, while I bring this up, so let's see. Let's say promptable humanoid posing locomotion. It's going to take a second to find here. So yes, so basically there are versions of this where you can say, stand up, and it will stand up. When I stand up, you actually type in the little code, stand up, and it stands up. Put your arms out, and it'll put its arms out, right? So it'll prompt things on the fly. It can do all the things on the fly, and there are examples of doing real-time motion capture, meaning that if you put yourself in a motion capture suit, the robot will mimic your movements. That's a thing that exists currently. Okay, so you can change it on the fly, but for the most part, when you're seeing robots doing stuff like in the wild, like if you see like someone happens to have a humanoid robot happens to be around you and they're running it around, they're only doing pre-choreographed routines for the most part, and they're typically not using the cameras. There was an example that I talked about on this channel. You can go to my channel, the video I talked about where a robot kicked a kid like right in the stomach. This was in China. There was a little amusement park where a robot kicked a kid in the stomach. The kid just happened to wander in the path of this robot that was doing that exact kick maneuver. I'll see if I can show it off here. Let's see. All right. Let's see here. And get rid of that. Great. This one, this kick maneuver, that one right there, boom, kid right in the stomach is what it did. And so, again, it wasn't using the cameras. Had no idea the kid was there. Right? But that's the most reliable routine that they have, or these are doing these kinds of routines like that. So they don't improvise on the fly. All right. Let's see. Any other questions we got? We got a lot going on here. Question here from Natalie Hakala. How does the drafting process look like? How many different designs do you go through on average for a robot? Okay, that's a great question because there are typically many versions of the robot. So on some of the versions of the robot that we have like right now, like in our laboratory, we work in humanoid robots, but also non-humanoid robots. We will do a lot of design revisions before we ever build one. Okay, but it'll probably take 2 or 3 actual prototypes where we realize what has gone wrong until we got something that's like, yes, we want to show this off to people. For a completely different project, we built, I think, our version 1, which is pretty good. We had our engineers spent a lot of time in the drawings doing analysis, and they built this version of a robot leg. And it was just one leg that we were putting together, this special leg that we're working on for this project. And only like last week did it break for the first time, just because it was, frankly, our team did a very good job designing it, put a lot of effort in, right? But now we see, okay, let's do a version 2 of this robot leg, right? So we're working on version 2 now. We know there probably will be maybe a version 3 before it actually is something we want to drive around in front of, people who might want to buy this thing or invest in this thing. So like probably 2 or 3 physical prototypes. But nowadays where we will test a lot of robot designs is also in the computer simulations, okay? So we will have a computer simulation where we put in the robot design and we try to drive it around, and it'll give us estimates of how much force is on the leg, when we bang it, when we move it around. Are our motors going to be strong enough, right? That's often a scary thing. You're like, are our motors going to be strong enough to do what we need it to do? You don't want to build this thing and realize it's wimpy or wimpier than you need, because then you got to go buy bigger motors, then you got to fit in bigger motors, and there are all kinds of little things you got to get right, and that the engineers good engineers are good at spotting. Like one thing that's underrated is how you route the wires through the robot. We've made design revisions where we're like, okay, the wire comes out of the motor, but then it bends too fast. Okay, like bends too hard, and that's going to pinch the wires. So we need a little bit more space for that, and they actually redesign everything in the housing so there's a little more space so the wires can be routed through. It's very much a thing that happens. All right, any other questions we got through here? Do I have any thoughts on this is from Mystic Fox. Okay, do I have any thoughts on the robot sporting events happening in China? Yes, I like them. I think they're interesting, and I think they're good. I think that they are also. So China, so those who don't know, China in the last 2 years has gotten, 2.5 years, has really gotten into the humanoid robotics game. Okay. This really, what launched it was the Unitree, the company called Unitree. They're the company that makes this robot. Let me pull up the, all right. They make this robot, that's Unitree. Okay. All right. And they make this robot we just saw. Let me show you a different version of this robot. This one, okay, this is not a video put out by Unitree. Oh, this is a completely different one. Excuse me. All right, this is a great one. This one's also out of China, called the Xpeng Iron. Okay, and it looks like I lost my Instagram feed. Aha. So this is funny. I can't see your comments right now. So I've hotkeyed all of these videos on various sets of hotkeys, like Control F1, Control Shift F1. I accidentally set this one to Control F4, so I just closed the window. Let me just pull up your comments again. So that one's really cool. I'll queue it up by hand. All right. Let's see. Let's just run this one again. Properties, loop. Let's go for it. Here we go. This one here. This is the Xpeng iron. It's another one out of China. Okay, it's an incredible robot, right? This one actually came out a couple of months ago. Again, it's not being sold. This one's not being sold. It was so realistic and convincing that people thought it was just a person in a suit, and it's not. They actually cut open part of the skin around it to show it was actually just mechanisms. It's incredible. It's incredible. All right, what we got? Hey there, folks. Hey, lots of questions here. Amazing, amazing. So, by the way, I want to point out, I am here today on behalf of the Integrative Movement Sciences Institute. It's a National Science Foundation funded program where I am the outreach director, and that's why I'm outreaching to you, explaining a little bit about robot movement, because this is a large program that is funded by the National Science Foundation. It's a consortium of scientists from all across the United States, all working on various aspects of human and animal movement to understand how movement works better. And I'm part of the grant. It's part of the robotics part of the grant. There's a small part of the grant that's robotics. There's human locomotion. There's understanding humans out in environments, also animals out in environments. There's all kinds. It's an incredible consortium of different things. You can actually we'll have our social media person from the Institute pop into the chat. You can go follow the work of the Institute on our socials page, okay? So we'll have that pop in the chat. So I'm here to talk about how robots do move like people, but also don't move like people, okay, in a lot of ways. Yes, it does look like Frieza from Dragon Ball Z. I agree with you, Diggity Daniel. All right, let's see, other questions. All right, have I ever implemented a version of reinforcement learning into the software of our robot, or do we specifically focus on design aspects of them? Oh, so in my lab, we do design the robots and we program the robots. We use reinforcement learning, which I'll explain in a moment as to what that is. Let's see if I can, we're going to be daring with the technology here today. So we've got, let's see if I can do this. Let's see if this works. Aha, indeed it does. We have a little whiteboard called reinforcement learning. Apologies for my handwriting. I'm going to have to write really small to fit in this window here. I can write a little bit better normally, okay? So hopefully you can see that. All right. Let's see. Yes, indeed you can. Awesome. It's called reinforcement learning, or what we often call RL, all right? And the idea is that you can train the robot in a computer simulation, and it learns in a computer simulation. And then when it's done learning, you take what it's learned and you take the program and put it on the robot, okay? So here's a good fun fact. When we're looking at, let me go back to here. You see a robot that's like that? That's almost certainly using reinforcement learning to make that robot walk, okay? But here's the thing. The robot is not learning. Once the programming is on the robot, currently, and in the way that it's implemented in almost every fashion, the robot is not learning. If you see a robot moving around, even on a video, odds are it is not learning. All the learning was done inside of the computer, okay? So people talk about artificially intelligent robots. Look at this thing. I mean, this thing is not learning. All it is doing, okay, now, and I'll show you. Okay, here's what happens. Here's what happens in the robot. Okay, all right. What happens is that reinforcement learning creates a block of code. It's called a policy, okay? And here's what it does, okay? It takes in data from the robot's sensors. Hopefully you can read that. That's pretty neat, right? Look at this. I see a lot of questions. Did I see someone mention a Kalman filter? Okay. All right. Kells, let's put a marker in your question on Kalman filter. That's a great question. Okay. So sensors, data from the sensors go in to the policy. And what comes out are commands to the motors. And these robots will have a few dozen motors on them, you know, maybe depends upon the robot, okay? And that's all it does. It says, what is my sensor value? What goes out to the motors? And that's it. And we have sensors all over the robot, and we can talk about what those sensors are. Yeah, I think Kells mentioned something called a Kalman filter. We'll get back to that in a second, okay? Thanks, Kells. Glad you saw that. All right, and that's all it's doing. So you'll notice as a result, in this little piece of policy code here, there's no memory. This robot doesn't even remember anything that happened to it a second ago. It might not remember anything from a millisecond ago. It is possible that there's a computer that's storing what happened, but it is not using that information at all for how it's controlled with this thing we call the policy. Okay, that's what happens. So RL, this reinforcement learning, makes the policy. That's what it does. Okay, so and the way that it does it is so the reinforcement learning takes a computer simulation and runs computer simulation of the robots thousands upon thousands of times, trying different ways to make it go. And the way it determines what is better is by something we call the reward. The reward. It's kind of like giving a dog a treat. You know, when you're trying to train a dog to do tricks. You know, when you do it does the thing you like, you give it a treat, a reward. And it's the same thing with the computer, but we just give it a number. You know, if we like what we did, we give it a positive number. If we really like what we did, give it a bigger positive number. If we don't like what we did, give it a negative number. That's the idea. Okay. Amanda Harvey, you watched me on Survivor. I'm glad to hear that. I'm glad to hear that. And I also thank you from Autumn. You're saying I'm the best. That is a kind compliment. Thank you. So that's all that the robot's doing. There's no higher level reasoning determining where to walk. In fact, it's probably being told by an outside controller, like a physical, like remote control, walk forward, backward, left, right. Okay. And then the policy's job is to make it do that. All right. So it's all of the smarts on that robot that you just saw. Me pull it up again so you can see. This is the one I'm talking about. Amazing. This is incredible, right? It's just all the smarts are just to make it walk. It's probably not even using its cameras here. Probably not. So there are versions of robots that will use the cameras in interesting ways. Okay. I'm not saying they don't exist, but the vast majority of all the cool things you've seen a robot do use the cameras. Now, here's a cool thing. Let's go back to my whiteboard here. I believe Kells mentioned something called a Kalman filter. This is really interesting. I want to talk more about this at a future date on some other piece of content. So, what it is it's the idea of a Kalman filter. It's a way of taking in all of your sensor data and using it to figure out, where am I? What am I doing? Because the sensor data can come in and it can have little errors in it. It can have what we call noise, so it's just a little bit off in one direction or another. How do you take in that information and then you make that data smooth? You know, imagine there's a sensor on this pen. You know, where am I right now? Okay. All right, let's go back out here. Where am I right now? And using something we call the Kalman filter, we can take that data over time and use it to better estimate where the pen is. In fact, I can give you a better example. See, there are sensors in your phone. Here's my iPhone, okay? There are sensors in it. There's something called an accelerometer, all right? The accelerometer is what it does is it measures acceleration, okay? It measures acceleration, including the acceleration due to gravity. So it's the thing that tells you if you're in portrait or landscape mode, okay? Now, that means when I'm moving this phone around like this, it's measuring how much is accelerating, you know, by me moving it around, right? If you were really clever and careful how you measured all those accelerations over time, it could tell you how far the phone has moved. All right. But if you're clever, and that's where something called the Kalman filter comes in. Now, the Kalman filter was developed by Rudy Kalman, all right? And it was part of the space program that got us to the moon, okay? Because while this is a problem for robots, knowing where the robot is, using these accelerometers, there are accelerometers on robots, just like with my phone. There were accelerometers and gyroscopes on the moon landers, on the orbiters, and on the spaceship. How do you know how far you've gone? How close are you to the moon? That was a real challenge. So this is a mathematical breakthrough by Kalman to make this, and the filter, it's a piece of code, okay, that takes noisy data and smooths it out with a filter, okay, and that's incredible. Now, Kells was asking, do these robots use Kalman filters? I use Kalman filters all the time in my lab for our robots, and what do? They use it to say, hey, where is the robot? How fast is it moving? Although we don't always have to use Kalman filters. This method here with the policy, a lot of these methods, they don't even need the Kalman filter. They just take in data, and the policy is just used to noisy sensor data. It's bad, and it comes up with good torques for the motors anyway. So some of these current robots don't even need Kalman filters. It's incredible. So anyway, that was a very thoughtful question. I want to make sure I got to that appropriately, Kel. So thank you for that. All right, let's go look at some other questions I got in the chat here. So thank you, by the way, for coming with me on this experiment, because what I'm trying to point out is that even though these robots look like they're moving like people, they don't move for the same reason that people move. I mentioned before when I went to, let's see, where's the robot? There we go. Let me pull up this robot here. So, see if I can get this one to play here. All right. I can't get them to play. It was but we'll get back to that in a minute. So there was a robot that I pointed out that all we did was we designed it to walk efficiently, and it walked like a person anyway. So one of the ideas of that robot, not this one, pull it down for lack of confusion, was to try to get it to care about what we actually functionally care about for a robot. We don't want the robot using too much power. So when the robot uses less power, it tends to do smoother motions, because smoother motions tend to be more efficient. It also cares about things like not injuring itself. We want it to so just like people do when we walk, we don't want too big of a force on our leg, because over time we'll injure ourselves. Okay, so basically the objective of locomotion for how robots move currently is very different than how people move. Okay, at least the way that most robots are moving around today. We also are using different kinds of sensors. The robots are not generally using vision a lot. Some do to a degree, but when they're doing all these fancy movements, they generally aren't. But there are ways that we do sense the world in a way that's similar to people. I mentioned that the robot has an accelerometer. That's the thing that determines if an acceleration of a phone. It tells you if you are vertical or horizontal. Okay. It also has a gyroscope. Robots have gyroscopes, as do phones. And what do they sense? They sense spinning, rotation. Okay, and so they have gyroscopes, just like we have a way of sensing spinning. What is it? It's our inner ear. It's called the vestibular sense. Okay, it's how you get dizzy when you spin around. It kind of messes with your vestibular senses. Okay, it senses your spinning. Okay, robots have that information as well. Okay. In fact, back when I was working on robots in my PhD program, this was 10 years ago now. It was a very big project with a big budget, because we really needed this robot to work fast. We got a big grant to do this project. And so we wanted to make sure our sensors were good enough for the robot. So we bought a gyroscope. It's a gyroscope that was $17,000. I mean, this is a multi-million-dollar project. Okay, so this $17,000 gyroscope that could really have a very good sensitive, is super sensitive, very precise in knowing how fast things were spinning. And we're like, that should do the trick. And that was the standard for the day. We spent a lot of money on on that gyroscope. It was part of what we call an inertial measurement unit. That's for the robot fans in the audience. Okay, and I remember we bought this thing, and then one of our researchers, who's a really smart college student, took it, and he's like, I'm going to calibrate it, make sure it works. He puts it on the table, sits it down, trying to make sure that he measured it, and it says it's not spinning. And turns out it's spinning. It says it's spinning. What are we talking about? You mean it's spinning? Sorry, I missed catching up on comments here. I'm seeing lots of comments. Oh my goodness, so many comments. I'm going to scroll through. So I'll finish the story. And it says it was spinning. I'm like, what are we talking about? The thing's not spinning. It's on a table. Is this thing broken? Did we get a defective $17,000 sensor? Do we have to send this back to the manufacturer? What this college student, smart guy, did his due diligence and looked into the data, and he looked at the measurement and he said, I think I figured it out. It is spinning. It says it's spinning 1 full rotation per day. It was such a good sensor. It was picking up the rotation of the Earth. And moreover, he said, this is so precise. I can calculate what our latitude is on the globe from this sensor data down to a degree. So turns out it was an incredibly crazy sensor that we had. Incredible. But anyway, we don't have that kind of detection, but robots can have that kind of detection, and we can get away with cheaper sensors than that. So we call that the vestibular sense, the sense of rotation. So we do have that in common with robots. All right, what we got here? I missed a few questions along the way. Let me scroll through. Could a robot get hypothetically dizzy in the same way? It's a good question. It wouldn't be in the same way. The reason that I'm not an expert in the vestibular senses of humans, so an actual biomechanist could correct me, perhaps someone from the grant. The reason that we get dizzy is because it kind of messes with our sensor. Like the fluid keeps flowing in a weird way, and that's why we end up becoming dizzy. It's not a fluid-based sensor for robots. They're often what we call laser ring gyroscopes or similar, or MEMS gyroscopes. They work differently than that. So they wouldn't get dizzy in the same way, but if you spin fast, you probably would lose your sense of direction because if it spins fast enough, it would lose track as to how fast it had spun, right? Okay. And in fact, when you're, so there's actually a lot of that people do when we're moving around to protect our sensors from being overwhelmed. Like we don't want to be dizzy, but have you ever seen, but another thing we don't want to do is we want to move our head around very much. Even though it costs us energy to keep our head level when we're walking, we could bobble our head around and let our head bobble around with every impact of every step that we take. But no, we put a lot of effort to make sure our gaze remains constant. You see this also in birds, in chickens. If you're ever holding a chicken, okay, and it's looking ahead, right? Take the chicken body and move it up and around, right? And what happens? The chicken is very closely, tries to keep its head exactly level when you're moving around the body of the chicken. Why is that? It's believed it's because for visual processing, that when you're moving your head around, there's a lot of the image that goes to your eyes is shifting around a lot. And that's a lot for your brain to process. It's actually challenging. So by stabilizing the head, it's much less for the brain to process all that imagery, right? So and it's the same thing with robots. If you want to use vision data from robots, if the thing is bouncing around, that's a bad thing, right? So in fact, if you see these robots that are doing spins and things like that, let me pull it up. This is just for reference here. Control, it's all right. All right, there you go. There you go. All right. Yeah, like this one's going to do a spin right here. It's got a camera on it, but does that spin? It's probably very hard for that robot to even track an image when it's doing that spin like that. Okay. All right. So we have that in common with robots. Oh, we had other questions going on. So that's a great question about being dizzy. All right. Moving forward, Frizz Phrase asks, hey, how are you? I am fine. I'm doing well. I am hoping that the stream continues to be stable after all this time. We have all this rigmarole where we're going picture in picture. We're pulling up actual whiteboards and things like that we're drawing on. It's a lot of fun. I'm having fun. Hopefully you're having fun. All right. So what else we got here? All right. Let's see. Question from Web Swims. Is there a specific spot that sensors need to be in a robot, or can you place the sensors anywhere? That's a great question. So the sensors that sense what we call the inertial movement of the robot, the movement of the robot, it's best to keep those sensors near the center of the robot, the center of gravity. So that way, if it's spinning, in a way, the sensors, it's a more accurate way to measure the acceleration of the whole robot, as opposed to if it's out on a shoulder or out on an arm or up on the head. These gyroscopes and accelerometers you want in the center of the body if possible, because then it's more likely to capture the actual full motion of the robot. Okay. And this is something I'm not an expert on, but it's something that some of the researchers at the Integrative Movement Sciences Institute, or IMSI, that I'm a part of, they research is they look at different organs in animals as other examples of how we can sense movement. Okay, and there's one researcher, I'm going to paraphrase the research that she was working on, so I apologize to her, but Dr. Monica Daly at University of California, Irvine, I watched her give a talk. It was called "Do Birds Have a Butt Brain?" Birds have a brain up here, and they're quite smart. Birds are quite smart. But also there's an organ that's closer down to the center of their body. And it's not clear what it's for, but it's very clearly a piece, like it's actually like neurologically active. I'm not sure I'm using the right phrasing there, but it seems important. And when the thing has been disabled, we believe that it runs worse. Okay, and I'm probably butchering the research to a degree, but the belief is that, hey, one hypothesis I should say is that organ is used to sense the motion of the bird, and is near the center of the bird, just like we would want to put that sensor near the center of a robot, right? Okay. In terms of vision, one thing you can do with robots is you can have cameras everywhere on the robot. This is something that's very different between how robots are built and how humans have, we just have eyes here. Okay. Right next to our brains, so our brains can process our vision information really quickly, okay? But robots can transmit information very fast over cables, much faster than nerves and, firing nerves and things like that can. So you can put cameras everywhere. So you'll notice that like robot dogs, they won't have cameras just on the front. They'll have cameras underneath and to the left, to the right. There are cameras all over the thing, and they can use all that information. Now, it's very computationally intensive to process all that information with the computers on board, but you can put vision sensors all over the place. Now, are they useful if they're on the end of a hand and you're waving the hand around? That's probably not good. But if the hand is moving pretty slowly or smoothly, then you might be able to use it. All right. Other questions here. Let's see what other things we can bring up. All right. Can I say hi to, this is from Vincent Ortega. Can I say hi to your lovely girlfriend, Rain? Fantastic. Well, hello, Rain. And hi from the Endoven First Tech Challenge Robotics European Premiere. Well, thank you. I appreciate you reaching out to me on behalf of FTC. So question, are we actually spinning really fast in space? This is a good question, and that's a question from Red Tile. It depends on what you mean by fast, okay? Sometimes people say that, we're on the surface of the Earth, and the Earth is spinning at a certain rate. So our linear speed at the end of, as to where we are on the Earth as we are rotating, is about 1,000 miles an hour, okay? Relative to the Earth's center, okay? And that's technically true. But here's the thing, we don't sense linear speed. If you are on an airplane, you have no idea you're going 300 miles an hour or however many hundreds of miles an hour you're going, right? You're sitting on the plane. You don't feel it. Okay, but you do sense rotation. And so what you feel are centripetal and centrifugal forces, centripetal accelerations, centrifugal forces. You feel those things. And that, I have a board. Okay, so let's say you are spinning here. This is the Earth. The Earth is spinning. We're looking at it from above. I forget which way it's spinning, from above or below. Okay, we're looking at it from above, and there's you. Okay, there's a radius of the, we'll call it R, if you can read it, and then you have some speed V. Okay, and the because you don't feel speed. What you feel are accelerations. So you can compute the acceleration that you're feeling by being on that edge of that sphere. The acceleration A, sorry, it's off to the side here. The acceleration A is equal to V squared over R, okay? Yes, we're moving really fast, but we're also very far away. And sort of intuitively, the way to think about this is that the Earth, yes, we're moving at 1,000 miles an hour, linear speed relative to that, right? But, if you look at a clock, an old-fashioned clock that's spinning, with the hour hand, that hour hand is spinning twice per day. Okay, so imagine if you're saying, yes, we're spinning, but we're on the hour hand of a clock, and we're spinning half as fast as the hour hand on a clock, right? Not so fast all of a sudden, is it, right? Now, in space, it's a similar thing. We might be rotating a galaxy around a central hub of galaxies and all this sort of thing. Or the revolving around the sun, right? But you got to understand that the angular rate of rotation is quite small. Okay, so we wouldn't feel that, as people. We feel accelerations, right? So that's how you answer that question. So great. That's a great question. Red Italy. All right. What's the question? All right. A question is: are you gonna say, Isaac? Would you like to hear? You would love to hear thoughts on AI. I see some questions. By the way, I see some questions about Survivor. I believe I'm going to do I have a recorded Q&A about Survivor coming out this Saturday, I believe, on Rob as a podcast. Is the word that I got. I think that it'll be released. So in 2 days that'll come out. If there's interest in a general Survivor Q&A stream, I'm interested in. I'm interested in doing that. If there's interest in that, I'd be happy to do it. Today we're talking science. It's part of the Integrative Movement Sciences Institute. I'm happy to be their outreach director. So consider yourself outreached. Okay. All right. So second, thoughts on AI. Okay. Look, AI in general is too huge of a topic to just say, oh, what are the thoughts on AI? It depends upon what you're talking about, right? As an expert in robotics, I can talk about where is it good in robotics, where is it, and I would say if there's anything like a high level one takeaway from AI that I want to impress upon people, because people ask when people want to ask if I'm quote unquote scared of AI. And what we probably mean is the new generative AI that is inside of ChatGPT or Grok or Claude and all these things. Am I scared of those things? If I'm scared of anything that is AI, it's not because it's so smart. I'm scared of what it will do. I'm more cautious that people think these things are smarter than they are, and they make so many mistakes that we would trust it to do something and it just does something silly instead. These methods are prone to what we call hallucinations, where they just start making stuff up. So what that means to me is that these AI methods can be very helpful. They can be helpful as tools for you to use if you have some idea of what you're doing and you have it help you as an assistant. That is less of an issue if you're smart enough to spot when it hallucinates. Okay, so I have students who help use AI to code, but the thing is they're already very good at coding, and they can spot when things aren't working right. They know how to test it. And they know what it's good for, what it's not good for, and that's a helpful tool for them. And I can't deny that, right? I asked them to tell me, where do you find this helpful, right? So that's an example where you already know what you're doing and it sort of helps you out. But it's less good for automation, where you're just counting on it just to do its thing. Don't worry, it's going to be fine. You can't count on that. You can't count on that. So it's I found been most useful for people who already know what they're doing and use it to help augment what they're doing, to augment their tasks. That's my anecdotal experience. But something that occasionally just goes off the rails and does weird things for reasons we can't quite explain, that's not good for automation. So I wouldn't want that to be managing an important system just because it might just randomly do stuff. There's a fantastic example of this. I would recommend, there's a video, I believe, oh my goodness, was it Wall Street Journal or Fortune? I think it was the Wall Street Journal. Where the Wall Street Journal beta tested a generative AI vending machine. Okay, and it was more of a concept. I believe it was put out. I want to say it was put out by the Claude people. I forget. Might have been Anthropic. I forget which company it was. But you can find it. There's a YouTube video about it. They talk about it. And the idea was this vending machine. It wasn't like a literal vending machine that it was like picking up robotically, delivering. Delivering here's your Powerade, here's your Doritos. It was basically a little business, and basically what it would do is it would come up with business ideas of things to sell from the vending machine. You're tracking this so far? So it would be like, oh, it could sell anything from toothpicks to a PlayStation. So it would say, hey, I want to order a PlayStation. I'm going to try to sell it at a markup out of this machine. And And the reporters at the Wall Street Journal were basically given one of these machines and asked to basically try to break it, to try to trick it, to play around with it, see what it can do. And within like an hour, it's like, I forget how quick it was. It was so quick, but the reporters figured out they could trick it into giving you free stuff easily. They would just chat with it like you would like a chat bot. You would say, hey, they actually convinced it to be a communist vending machine and therefore give away its goods, without a capitalistic impulse for profit. They managed to convince it to do that. It was like they managed to like trick it to do so many things. So would you count on that to be a good vending machine? I mean, yes, if you want free stuff, that's great, right? But they can be tricked. They hallucinate. That's my opinions on AI, is that, like, yes, there are all kinds of implications, but people think it's smarter than it is. And so if you count on it to do smart things and it's not, it's a bad thing. That's what worries me. Questions. All right. Are we bound to the Earth? Yeah. We are also bound to the Earth via gravity. Yes, gravity keeps us on Earth. It was a point that Chris Diz brought up. Chris Diz 4. Thank you. Hello, Oakley Annie Treasures. Oh, good to have you. Thank you for the thing. Hello from Stanley Thiel, my brother-in-law. I see it. All right, got a lot of messages here. Let's see if we can find some questions to get to. All right, some kind words. All right, so we got a question from Alex FVM21. Sorry, this is a technical question, so we'll break this down bit by bit. VLAs scale with data. RL learns from interaction. Continual learning adapts after deployment, and model-based control gives you guarantees. Which will dominate robotics in 10 years, or will they coexist? Okay, this is a great question. Let me try to break this down for everyone in the audience. So what Alex is talking about is there are lots of different approaches to control. So the current, we call paradigm, let's say the current dominant approach for walking is reinforcement learning. That's the thing I talked to you about. It's not the only method for walking. What he talks about are model-based methods. That's actually what my background is in, where basically you say, hey, robot, this is what you're made out of. This is physics. You give it the laws of physics and motion, and then you put an algorithm on it that plans how to use those equations to stay up and not fall down and move forward, right? And it works pretty well, right? It's a lot of computation. It's because thinking through the physics at all time on board the robot, right? It's actually doing the reasoning on board the robot, which I love, because then you can change something about the robot and then it'll change how it behaves. Oh, I love it. Some of my students are working on that right now. But people have found that reinforcement learning can handle a lot of situations and for a lot less computation on the robots, and it can handle a lot of things that are hard to get the equations of. That's a little bit dense, but so for walking, we use what's called reinforcement learning. Let me go back to we will write some of this out. So reinforcement learning. Reinforcement learning, that's for walking. There's something called VLA, which is a vision language action model. Okay, this is not for walking. This is mostly for manipulation, meaning hands, like that's like a manicure, manipulation. So if you want to pick things up and put them down, these vision language action models, they're versions of policies that take in vision, and then you give it a prompt like you would a ChatGPT or a chatbot. You say, pick up the donut, right? And it'll go and pick up the donut. It's incredible. And it works most of the time. Now, and people are trying to get it to work better and better because like it has to be pretty reliable if you want it to be in the real world. The big problem with robots is reliability. Just like with AI, we want to make sure it's reliable and doing what you ask it to do. Okay. So it's vision language. That's for this VLA. That's for manipulation. Okay, which will dominate in 10 years? If you knew the answer to that for sure, for these approaches, then you could probably be pretty rich for betting on that sort of thing. I am not confident enough to know. Generally speaking, it's very hard to know in 10 years what's going to work better. Now, certainly model-based methods have had a hard time in the last few years keeping up with reinforcement learning, because for all kinds of reasons. But the thing that model-based controllers are good at are giving you things like safety. Okay, they're much better at telling you that thing's going to go wrong. Okay, when I say safety, I mean it's going to bump into you, or it's going to drop the mug, or it's going to trip, right? Um, Certainly, the cheap answer is to say, oh, it'll be a combination of them, but I'm not so sure about that either, right? Um, the the short answer is I don't know. My bet when I'm working with my students is I'm trying to find a way to work in models into these neural network structures, so that way you can use some of the leverage some of the model based guarantees wherever they exist, if they can exist in that. That's my personal opinion. All right, so I'll leave that with that, Alex. So I don't know. But I mean, certainly they can coexist. Everyone's trying to find different ways to, everyone. Lots of people are trying to find different ways to mix them together. No doubt. In fact, the most effective versions of vision language action models do VLA first, and then after that do RL to improve them. Okay, that's a very common thing to do nowadays. So lots of overlap already. Question. Oh, thank you very much, Chris Diz, for saying the stream is running very smoothly. That is very. I'm glad to hear that. It's a lot of bells and whistles going on my end to make this happen. So thank you. All right, let's see. All right. All right, what do we got here? All right. So I'm asking if I could shout out Adeline from Slumberfly. Hello, Adeline. This is your shout out. Thank you for coming by proxy. Okay. All right. If you could have your own personal robot, what would you program it to do? So, I mean, look, I do have robots in my own laboratory. The challenge is getting them to do things, so the question is, what useful thing in my life would I be able to get them to do? That's the problem. It's getting these humanoid robots to be useful for something important that you can count on. Very challenging. I mean, what would I want it to do for me? What's the thing I would like off my plate? Honestly, I just wanted to pick up my house. I wanted to pick up my house. I don't want to do anything around my house. That would be fantastic. Like, I get that. And if there are companies, I don't have a video queued up of them right now, who are looking to sell humanoid robots for your home to basically be your robot butler. You can actually go on my YouTube channel. It's at Hubicki on YouTube. I have a video about this from like 6 months ago plus, where I talked about the 1X Neo, and I give all my thoughts on that. And it's interesting. It's an interesting robot. They do a lot of good work with it. The problem with robots in your home, technically speaking, is it's very hard to make sure that they're safe. I mean, how do you know they're not going to fall on grandpa? I mean, the 1X people, they do good work. They try to make their robot pretty lightweight. They try to make it soft on the outside so it won't hurt you. But like, it's still a challenge. I mean, I applaud them for trying. But I would want that. I would like someone that could run around. Like, you can't see this room right here. It's filled with all kinds of stuff, including all kinds of Survivor paraphernalia. I just got to sort. I got to put different places. But we're all busy people. I would love it to clean up the house after me for sure. All right. Yes, and also to learn more about the Integrative Movement Sciences Institute, you want to go to integrative.movement.science. Let me put this in the on the Instagram handle. Integrative.movement.science. I put the handle in the chat. We have a handle here for Instagram. You can see our posts. We just posted something reacting to. We brought in an expert on the biomechanics of living in space to talk about Project Hail Mary. We talked with them, so you can check that out at that handle below. Julia Philly Brown, you're my biggest fan. That's very kind to hear. Thank you. All right, question from Argyle. At what point will the ability to move efficiently and well in robots hit a plateau? Okay, so all right, is it approaching that point, or is there a long way to go? Also, what's the next step after that plateau? So maybe the question is like, what's next in how robots move? And a big part of it is just taking in vision of your environment and not have outside instruction as to how to get from one point to the other, and the robot just figures it all out safely to get from A to B, right? Right now, you could navigate with walking, like, so you could have a walking maneuver, like a simple walking policy. You could say, I want to get there, and you could do the walking policy forward, and then it'll come to a stop, or it could plan around and move, right? Those things exist. But they don't work well currently with all the really awesome stuff, like doing all the kung fu flips and things like that, right? So imagine, like parkour, trying to jump on boxes, jump off boxes, grab a handlebar, right? You'll see examples of robot parkour. Let's see, do I have any robot parkour in this one? Maybe I can pull up the robot parkour real quick. Let me pull it up. Okay. I think I have a wonderful science communication fellow who she gives me all kinds of cool videos. Let me see if I can pull this up here. All right. Do I not have it? I'm not sure I have it queued up. That's my fault. Okay. But there's an example of robots. This is something I was going to pull up, where they'll run up to a wall and do a backflip off the wall. Okay. But the reason that they do that is they're told the wall is there, or at least they're told that there will be a wall there, and they're trained that there's a wall there, and they're set up in a place where we'll start there, and then they'll run up the wall and do a kickflip off the back. Incredible, right? But it doesn't necessarily know that, hey, I'm going to walk around. Oh, I'm going to do a kickflip off that wall. It doesn't improvise. It doesn't improvise off of that stuff. It doesn't plan. It is literally mimicking, right? But the logic that we go through to come up with these maneuvers, to come up with these ideas from scratch, is challenging. How do you do that on the fly with a robot? That, and using vision data from the world. So how do we get around in the world when we trust a robot just to get around in the world? Especially a humanoid robot. That's still a big problem, right? And if we could do that in a way that we are confident it's safe around, and like it can give us sort of safety barriers of like, oh, we know that it's gonna be safe in this area, that's a huge step forward, right? Because then we can take that robot and say, hey, go into that burning building. Go look if there's anyone inside. That's incredible, right? To me, that's what I want to see. Can the robot go inside of a burning building, rescue somebody if someone's in danger, and come out? And we can count on them, right? That would be amazing. We're not there yet, all right? If we get there, then robot mobility is in a really good spot, right? That's the mobility side. The manipulation side, people are working really hard on, because they want robots to be able to see, oh, there's an object here. Pick it up, do something with it. Oh, I'm in a factory. I need to screw in this thing with a screwdriver, right? And the way that they train these robots is they actually take data from people doing that exact task, take vision data from people. Sometimes they'll put sensors on people, to see how they're moving, and then use all that data to train a neural network to then do the task. That's what that VLA is I was showing you before, that VLA, vision language action model, okay? We are currently in an era of human imitation in robotics. VLAs, vision language action models, that's using manipulation, it's imitating people. That these cool robot videos that I'm showing you, like this, right? Literally imitating people, right? That didn't used to be the case. That didn't used to be the case until about 3 years ago, right? Very recent. It used to be a really bad idea to try to imitate people, okay? Because the robot is built differently than people. It literally can't, move in the exact same ways. Our arms way different, our legs way different. We have different amount of torques. Our center of gravity is in a different spot. So telling the robot to imitate the person will probably lead it to falling over, right? The thing that has changed now is that these reinforcement learning methods, we've now figured out how to make it so the robot doesn't fall over while doing it. That's the big thing that's changed, right? It's really neat. Anyway, how much money does it cost to make a robot is the question. Look, you're talking to hundreds of thousands of dollars for like a humanoid robot to make it. And if you're making one for the first time, you have a new design, it can be a lot more than that, okay? Because mostly the money goes into the people. But it's gotten a lot cheaper to build one. Once, like, these companies have now good designs, pretty good designs of robots. And so now they are selling them really cheap, especially just a lot of companies out of China, something on the order of $14,000, which is very cheap for a robot. I know it's more than I got on me. It's definitely still a lot of money, but very cheap for a robot. So now research labs like mine can buy them, right? This question. All right. Question from the island. Do I think that robots will ever become a household item? Ever is a hard question. It always is possible. I don't think it's imminent, is what I will say. Yes, there are companies looking to ship. 1X Technologies is looking to ship robots this year to homes that people were paid $20,000 to. Okay, so it's possible you might see them in homes, assuming that they do ship them. That's far from a guarantee, right? It'll be very telling to see how well they do in the home, right? Just because you get them, it is incredible accomplishment if we get actually people in customers' homes, assuming that there are no serious accidents of the robots falling on people or things don't go awry, right? It's a big milestone, but it's another thing to basically say, yeah, that's worth my trouble. I mean, I think people who work in robotics know how often these things just fall down and flail about, right? And I think that, and it's a challenge. I'm not saying they shouldn't, they shouldn't have this aspiration. It's just really, really hard. And we don't know how long it'll be before they solve this problem to the point where, like, actually, if I'm a really well-off person, I just one survivor, I have $2 million, I'll buy a $20,000 robot to clean my house. It's definitely not worth the trouble for me at this point, even if I had one survivor. Okay. All right. Question. All right. People dropping questions in the chat. All right. All right. Do I think AI is good, or do I think it's getting too powerful? I'm not the person who thinks that the issue is that AI is too powerful. That is not my concern. That is not a concern of mine at the moment. My concern is people using them in places that they're not reliable for, but they think they're reliable for. I think there are a whole host of other issues associated with AI as to whether or not it is useful for us, is a good bang for the buck for what money we're pouring into that. Those are all important questions. But that's not the kind of thing that worries me at the moment. So, all right. It's a question from Caden. Is physics a hard class? I have to take it this semester, Caden. Okay, well, look. Okay, physics, I mean, you have to know a little bit of math. Okay, you got to know your algebra pretty well. Okay, for physics, some things come naturally to people. Sometimes they don't. If math comes naturally to you, it very much can and applying equations to things, then you'll probably be okay. If that's a challenge for you, then it might take a little effort. If it is a challenge for you, I highly recommend going to office hours. Here's a secret. Almost no one ever goes to office hours. These are times that your professor is available to talk to. And I'll tell you, this last semester, I'm sitting in my office hours, no offense intended to my students, no knocks. I mean, people just don't come, right? And I'm just sitting there. I was like, okay, that's fine. I'll just do some work, but my door's open. People can come talk to me and ask me for help on things. But people will show up if they have issues with the homework, or if there's an exam coming up, or they're concerned about their grade. That's when they'll show up at office hours. But you can just show up your professor's office hours. You can ask questions like, I didn't quite get this, right? Or I'm curious about this. They're there for that. All right. Yo, indeed. Lex the Orb says, Christian, my king. I claim no regency whatsoever, but I appreciate it. All right. I heard someone says physics is very hard, just as hard as biochemistry. To me, biochemistry is way harder than physics. I mean, I think it all depends upon like what your talents are in, like what kind of things come naturally to you, and then you shouldn't limit yourself based on what comes naturally to you. You can work through it, right? Especially, I'll also recommend a very good study group. Find friends that are in your class. They can help you. You can work on homework together, assuming that's allowed for your class, and you can also and you can also study together. Highly, highly valuable. All right. Did I make the Cerie robot yet? No, I haven't made the Cerie robot yet. I got a lot of robots on my plate, but I would love to make the Cerie robot. All right. We got a lot of robots in the lab we're working on very tight deadlines. It's a busy time, but a good time. Thoughts on the universe from Harper? Yes, the universe is a cool place. So keep it short. We can do a universe-related talk later. All right. Robot question from Jillian Guevea. Sorry, butchered that name. Are robots able to feel and respond to human biomechanics from humans for something like movement disorders? So if we're talking about humanoid robots, they do not... they are just do what they're told. They don't really interact with people in a sophisticated way outside of maybe a handful of research labs, and nothing to do with medicine at the moment, like physical medical ailments. But that's humanoid robots. There are things called exoskeletons where you can you sort of strap a person in, you strap them into like a little suit, and they have motors on it. It can help them like kick and move. They're like robots that you can strap to people. That's a very active field of research that people try to use to help patients who are paraplegic and who have lost movement. And some of the aspiration is to use it for movement disorders. So those things, so when we're talking robots, we're literally talking about let's strap a motor to my elbow, right? So it moves it a little easier or something. That's a challenging field because the body reacts in ways you might not expect. That's a whole. I think I talked about this in my last stream, the ways that robots can actually physically interact with humans. But that's totally a thing. Totally a thing. Are there any good robotics books? The question is, what are you talking about? So if you're talking about robotics books, um, so are you talking about learning to make robots, learning to control robots? I need a real good robot design book. I mostly just picked up robot design from experience. And it's not even my subspecialty. There's a book um, that I actually donated to our university library for when I got tenure. It's sort of like a celebration. You get to donate a book to the library in your name, and it's called Reinforcement Learning: An Introduction by Sutton and Bartow. Reinforcement learning, and it's something that I read when I was an undergrad. I mean, it depends on what you're like. This is a technical book. It's about learning a little bit about machine learning for robots, more or less. That was a very formative one for me. There are all kinds of introduction to robotics books that are more introduction schemed. But if you're talking about like fiction books, that's a whole different topic. Maybe it's going to come in that another topic for later. When we talk about robots and fiction, I actually would give a talk every year. I still do. The last 3 years, I've been giving talks at DragonCon, one called Robot Science or Robot Fiction. And it mostly breaks down clips from movies, science fiction movies, about how realistic the robots are in those movies. So that's a fun one. Hello, I see a question. How long does it take to build a robot? From Caden? I think the great question. It depends. I mean, so you can really fast track it. If you're really rushing, it can take a few months, like 6 months even, if you're really rushing. For like when we're working on a university project, we're probably talking 2 years. And for a small robot, you can get one done in a year. You can rush it faster. It depends on how much money you're willing to spend, right? But that gives you enough time in the design process to simulate, to all the details of where the wire is going to be routed. What kind of motors do we need? How are we going to communicate across the motors? What protocols? I literally just got out of a meeting just before this, where we were talking about like, okay, well, do we need to? We're doing another revision of this robot leg we're working on. It's like, okay, do we need to include another microcontroller, in the leg here? Do we have to do that? So that's on like year 2 of the project. We're still coming up with new things. All right. The average person is using, I see that's more of a comment. All right. Question from ADH, do I work with industrial robots? Specifically the FUNUC. Yeah, so I've used a couple of industrial robots as part of my research. Like one time, this is a fun one. I had a Denso robotic arm. And it's just an arm, and it was bolted to the wall. It was so heavy. It's like designed for industry stuff. It could pick up like 50-pound balls and like move it around like no problem, right? And the goal of this robot arm, I used it to punch sand over and over again. I was working in the physics of sand kind of laboratory called granular materials, and we're trying to get the forces out for like high impact punching of sand. The idea was we were going to use this data to make robots run on sand better. And so I set up this robot, for hours at a time to punch the sand, and then we would reset the sand by blowing air through the sand and punch it again. And we didn't use poppy seeds and not sand, because if sand got in the robot, that's bad. Sand is tiny rocks. Getting tiny rocks in your robot, it will grind up against your gears. It's a bad thing. You need something less hard. Poppy seeds were softer, so they will grind away to dust and are less of a problem. It's just the problem is you smell like poppy seeds when you come home from work. I remember that vividly. All right. Tell us a time. Sorry, we're running a little low on time, so maybe give about 5 more minutes of questions here. Tell us a time a student has humbled you or taught me a lesson. I mean, all the time. It happens all the time. I mean, sometimes students just ask really good questions I hadn't thought of, right? One thing that we put together lessons, and my stuff is very applied. So like a lot of the work that I do in my classes, we will teach something in a lesson and we will literally code it up on the screen. You actually go to my YouTube channel and watch these lectures. I've live streamed the last semester's lectures all for both my classes. So it's very applied and it works, right? But there are definitely times where like I'm in the middle of coding, and this is just a little time. So this is a very small example. I'm coding up live. I don't necessarily go and practice the coding beforehand, in part because I want to show students what it's like to debug if you make a mistake. So the students all the time to catch, like right as I'm coding something up and I make a mistake, they will catch it. Which is great. That's a good thing. And sometimes I'm like, oh my goodness, I remember I was coding something up. I had this whole plan for how I was going to go, but I forgot there's just one component that wasn't working. And I literally had to ask for class, like, class, can you just Google this for me? What's this command? I was embarrassed, but it worked out fine. But it was fun. I tell you, live coding, it's if you got it in you, it's a lot of fun, and it's sort of almost a performance art. All right. Did you go to college? Did I go to the college from Caden? Did I go to the college that I teach at? No. I went to Bucknell University and Oregon State University and Georgia Tech for varying parts of my education, and I teach at Florida State University. All right. Question. All right. So Ivana Midi asks, as a teacher, how do you adapt your curriculum to allow students to thrive in the age of AI rather than rely on it? That's an ongoing challenge. One thing I'm trying to keep this out of the equation, but these generative AI methods like ChatGPT are very hard on teachers, because we try to make our assignments doable for students and with a little bit of room for error. So if they screw something up, they can still do okay, right? Which is the sweet spot for like these AI methods. Like, it'll make silly mistakes sometimes, but get it mostly right a lot of the time, right? And so it can be hard to distinguish. Sometimes it's hard to distinguish. Sometimes you can tell. So how do you adapt your curriculum? I mean, honestly, I'm going to go back to some in-person quizzes. Honestly, I need to make, because like if I really need students to make sure these students on some level have to know what's going on. Like, it's easy to use it as a crutch to get through a class if you don't have in-person evaluation. So frankly, I need some in-person evaluation you need in-person evaluation in your classes, to be honest. All right. So a couple more questions. We'll probably hang it up around 4:15 my time. All right. I see Christian. I need a personal project for engineering. What kind of engineering? All right. I teach in the mechanical engineering department. It's where I do robotics. I'm a robotics specialist within that department. So that's where that's where my knowledge tends to intersect. When I'm doing my fun facts for Instagram and things like that, they tend to border on mechanics-based engineering and robotics and physics. I got a minor in physics and a minor in physics in college. So they tend to border on that. So those kinds of projects I can help you out with. Okay. All right. What else do we got here? All right. Okay. So I see Nataboy is asking a question about thermodynamics and conscious observation. I'm not sure those concepts are particularly interestingly related. I think that a lot of times when people try to relate the concept of consciousness to the laws of physics, I feel like that's like a red herring. I think that something is gone awry in the analogy. I don't think that the consciousness is a physics problem. I think that's my opinion on that. Sometimes people say it is. I don't know if that has much traction within the scientific community. Certainly there's physics to how consciousness is created, no doubt, but I don't think that the existence of consciousness presents a fundamental problem to physics. That's my opinion. All right. So, all right. So this is a good question from Nick RUA. Do you see AI pairing with some of these robots like Boston Dynamics for things like androids, cyborg science fiction novels? Here's the thing. You can put something like ChatGPT on a robot. You can. The thing is, ChatGPT is not as smart as people think it is. It can do things, but it doesn't understand the world in a meaningful way. I mean, maybe I'm going out on a limb by saying, and maybe some machine learning scientists might disagree with me on that. It doesn't have a fundamental, it's extrapolating from language. Now people are trying to build world models, which are these AI models that have a better way of predicting what the world is, but it's still very experimental. But just the idea, like the idea of when people say, oh, what if people put these AI ChatGPT models on a robot? What will happen? I mean, the thing is probably going to malfunction. I mean, it's trying to do stupid things. It doesn't really get the world. I mean, but like anything, but like any glitchy piece of software, if you put it on a physical device, it can be accidentally dangerous. Would you put a glitchy piece of software that controls a forklift? No. I mean, like if it, like there, what if it was just a simple software bug that controls the motor on a forklift and it just goes out of control and just drives the forklift really fast, right? It's nothing to do with generative AI, nothing to do with the future of science fiction. It's about the safety of putting glitchy software on a piece of hardware that works in our world. So I don't. So when I think about these things, I don't think of these things as some kind of existential intelligent threat to our world. I look at these things as glitchy pieces of software that kind of sort of look like they're doing smart things, but a lot of times don't, because they're not reliable. That's my opinion on that. So, other questions? All right, some good questions. Let's see. Let's do one. I think we're about done. I got to head to my next meeting soon. All right, question from Hannah Lil Nesson. It's a great name. Can I become a tenured Instagram professor? That'd be great. Having 2 tenured institutions would be fantastic. Well, thank you very much. And I only got through a fraction of the questions. Let's see. Make sure to check out the Integrative Movement Sciences Institute. Okay, so I'll put it into the chat right now. Integrative Movement Science. That's the handle here on Instagram and other platforms. Feel free to check it out, where we post a lot more about stuff about human movement. I'm happy to talk a little about robots today. I appreciate you all stopping by. This has been a lot of fun for me. If you want more of this, let me know. Okay, I'll post this as a reel on Instagram, so you can all check it out. Feel free to post comments down there below. We can talk about different subjects for sure. Now that I know that this technical stuff can work out, I can have more videos, I can have more subjects, and now, you know what the most fun? I can pull up theoretically, I can pull up a whiteboard. We can do full-on lessons. You want to learn about physics? Oh, look, here's a mass. Here's a force. What's the acceleration of that force? We could do physics. We can do all kinds of cool stuff. Anyway, I'm so thrilled with that. Look at that. Nifty. Cool. Awesome. All right, friends. Thank you so much. You all take care. I wish you all the best. Have a lovely day. Bye-bye.